Okay, so in the previous video, we have seen how we define probability mass function. Okay, now this would be the table for a discrete random variable. I just forgot to make a note of this in the previous video. That is, now here the column sum I'll be taking, which would be column sum would be P1, P2, P3. Similarly, I'll be taking the row sum P1, P2, P3, P4, I'm sorry. Finally, the sum of all the probabilities row-wise or column-wise should be 1. The basic axioms of probability should satisfy whatever we do. Okay, accordingly, the probability mass function is defined. Okay, there's another version of defining probability mass function for a discrete random variable. This is from Gupta and Kapoor. This definition is from S.C. Gupta and Kapoor, which is a standard one. If capital X comma capital Y is a two-dimensional discrete random variable, R dot V can be used. Okay. That's a universal notation or shortcut. Then the joint discrete function of capital X and Y, also called, as we have said, also called joint probability mass function, joint probability mass function. Basically, first one or two videos are for definitions because we are again shifting to 2D. So if you're thorough with the definitions, then problems can be easily solved. So make sure you listen to the definitions and then proceed with the problems. Called joint probability mass function, capital X, capital Y, denoted by P suffix X comma Y is defined as P of XY, XI, YI. This is equal to P of capital X is equal to Xi, comma, capital Y is equal to Yj, I can say, for a value of Xij, for a value of Xi, Yj. Okay. Different ways of defining it. If you are thorough with the different ways of defining it, then obviously things will follow. I mean, when you are doing problems, easily you will be able to categorize and solve. Okay. P of Xi would be capital X being equal to Xi, capital Y, I'm sorry, Xi, Yj would be capital X being equal to Xi, capital Y being equal to Yj. Okay. For a value Xi, Yj. If it is not like that, otherwise, how will I define it as Xi, Yj is equal to 0 otherwise. Okay. Yeah. So this is another way of defining it. You will understand while doing the problem why this version is also needed. Okay. Otherwise, its value would be 0. If X is equal to Xi and Y is equal to Yj, then P of capital XY, Xi, Yj is defined to be capital X is probability of capital X is equal to Xi, Y is equal to Yj. Okay. Otherwise, if it is some other values, then it would be 0. Okay. Yeah. After this definition, there's one more which you ought to know. There are actually three proper definitions. First, the joint probability mass function, how it is defined, you should know. Marginal probability function, if you need to know. Conditional probability for two dimensions, two variables, you ought to know. Once you know these things, you'll be able to do problems on it, whether it is discrete or continuous. Okay. Marginal probability function. Marginal probability function. How do I define it? Okay, it's nothing but the column sum, guys. It's in short, if you ask me what exactly is it, it is just the column sum or the row sum kind. Okay, that's what I can say. But anyways, let me go with the proper formal definition in case if you are asked to define this for 2 marks or something, you know it. Let capital X comma Y be a discrete two-dimensional random variable. R dot V. R dot V is a universal shortcut. You can use it even in the exams. R dot V, which your prescribed book also uses the same shortcut, which takes up countable number of values. Again, all of you countable number of values. All of you should be aware of what is countable, guys. Countable means what? Don't think it is just I'm able to count it, so it is countable. No, no. Countable has a proper definition. What that is from the set under consideration to the set of natural numbers. If I am able to find a one-to-one mapping, if I'm able to map the set under consideration to natural numbers, the natural numbers set by a one-to-one mapping, then I can say it is countable. I cannot count it, but then I can map every element in the set S to an element in the natural numbers. That doesn't happen with real numbers or irrational numbers kind of things, because real numbers it doesn't happen. So because of which real numbers are uncountable. Okay. A set of even numbers, set of odd numbers are all countable because you can find such mapping. Okay, just Google it, what exactly countable is. Not just by the normal word, it has an inner meaning. That is, you should find a one-to-one mapping from the set under consideration to natural numbers. So that's what they are saying, that they need not be finite in number. But if you're able to find a one-to-one mapping, if you can map every element of the set S under consideration to the set of natural numbers, then the set S is said to be countable. Okay. So if capital X comma capital Y be discrete, be a discrete two-dimensional random variables which takes a countable number of values of xi and yj, then the probability distribution. Then the probability distribution probability distribution of X determined like this, as follows. Determine as follows. How? I'll just show you. See, probability distribution of X determined as follows. How? P of capital X, xi is the limit. Okay. P of capital X is equal to xi. Xi is the limit, guys. So what I'll be doing, just see here. P of capital X is equal to xi intersection y is equal to y1. From the above table only I'm taking. P of capital X is equal to xi intersection. Of course, let this be some x4 or something like this, or x2 also it can be. Let this be x2 or something. Okay, then this is x2 intersection y is equal to y2 plus P of x is equal to x2. x2 is fixed. Y is changing. Okay, y3 plus P of x is equal to x2 intersection y is equal to y4. Understood? I'm adding all the probabilities row wise. Okay, from the table. That would be, let me give the proper definition. Now see, x is equal to 2 is fixed. Okay, I'm calculating for y is equal to 1, y is equal to 2, y is equal to 3, and y is equal to 4. Okay, all those, and I'm summing up. Okay, so row wise sum or column wise sum. If it is column wise, then y will take the values. If it is row wise, x will take the values. Okay, yeah. Row wise sum. Okay, this can be written like this. This is nothing but P21, P22, P23. I have taken particular because it's understandable to you, to be easily understandable to you. Okay, or this is equal to summation j is equal to 1 to 4 P1j. No, P2j. Okay, yeah. Or this can also be notated as P2, just P2, as I've given the notation there on the table. You can just look at it. Okay, this would be called, this is called marginal probability mass function. Marginal probability mass function. Mass function of x, of course, because I'm calculating it for x. Or this is also called a discrete marginal density function. No, marginal mass function only. Marginal mass function, discrete marginal mass function, of x. Okay. Similarly, for y, you can do, guys. How I can do for y is I'll just be writing P capital Y, small y, j. This is equal to P of capital Y is equal to yj. How do I do it? Of course, ji can fix and take some value. Otherwise, how I'm calculating? P of x is equal to x1 intersection P of, no, not P. Y is equal to yj plus P of x is equal to x2 intersection P of x is equal to x2 intersection y is equal to yj, and it goes on and on, plus P of x is equal to it has gone till I think x4 intersection y is equal to yj, where j accordingly where j ranges from, accordingly I'll be writing. Or this can also be written as summation I is equal to 1 to 4 actually under consideration, right? P of I and then j, right? Ij, if j is fixed, I will write the value of j. Okay, accordingly I will take, or this would be called P dot P dot j I will be writing here also. Just a small correction here. Not exactly P2, P2 dot it should be, because j is varying and 2 is fixed. Here also j is fixed and the other values are varying. I'll be putting like this. By the way, what you ought to remember here is it is called the probability, new notation, new terminology. Marginal probability mass function is the word that we'll be using here. Yeah. In the next video, we will be seeing conditional probability for two-dimensional variables. Okay.